In this video, we're working a problem with a man standing on an inertial platform. So you have a platform like this, a rotating platform, and you have a person, and they have a couple of bricks, it says. And the key thing about the platform is that the platform is made so that it rotates without providing any torque. So the sum of the torques is equal to delta L over delta T. But there are no torques, so therefore delta L is 0. So this is a conservation of angular momentum problem. Energy is not conserved. So you don't want to use conservation of energy. There's somebody doing non-conservative work. And I'll show you that that's the person. We're not counting all the energy, such as the energy inside the man's body, who's enabling this thing to work. And so what happens in it is that we need to match up the initial angular momentum to the final angular momentum of the system. And we can write that as the initial moment of inertia times the initial angular speed, and that has to equal the final moment of inertia times the final angular speed. Now, in this problem, they've given us all of this information. The initial speed was 0.9 revolutions per second. Now, I will admit that in most cases you want to convert that to rads per second, but because of the way this problem works out, it's not going to be necessary, and I'll show you that in just a second. So omega I 0.9 rev per second. What else do we know? It says that when he's on this thing initially, he has the bricks being held out, and his equivalent rotational inertia is 5.5 grams per meter squared. So we have I initial 5.5 kilogram meter squared. And then he brings the bricks in. Now he doesn't change his mass or the mass of the system by bringing the bricks in, but he changes the R that they are about the axis of rotation. And so he makes it have an equivalent smaller moment of inertia. It is the moment of inertia, not the mass, that is what is determining this way that objects rotate. So this is only 2.0 kilogram meter squared. And then it asks, what is the final angular speed? Well, omega F is equal to the moment of inertia initial times the original angular speed divided by the final moment of inertia. This is 5.5 kilogram meter squared, and divided by 2.0 kilogram meter squared, and then multiply all of that by 0.9 revolutions per second. And then we punch a calculator to find out what the final answer here is. But we can see that 5.5 is more than twice 2, so we're going to increase the speed by more than a factor of 2. And we find it's 2.48 revolutions per second. So he speeds up. Notice the reason I didn't need to mess with this changing the units is that these two i's, their units canceled, and so I'm going to be in the units of whatever omega initial was. If you were going to find a torque, if you were going to find kinetic energy in joules, if you were going to some other type of quantity, then you must convert the omega into rads per second. But if you're just staying from one form of omega to a later time omega, then you don't, because all the other units cancel out. Now, let me show you this demo and show you that the person will speed up when they bring in bricks. In our case, 2 metal weights that the student is holding, when they bring them in closer, how they speed up, and when they put them out, how they slow down. And the only thing they're doing here is keeping L constant. So if I goes up, omega goes down. And if I goes down, oops, let me change colors there. Meant to change colors. Omega goes down. Sorry, I goes down, omega goes up. Now I said kinetic energy is not conserved, and that's because the kinetic energy is L squared over 2I. And this is a better form than 1/2 I omega squared. Now let me show you why it's a better form. Since L is a constant, initially and final, the numerator doesn't change, only the denominator. So if he makes his I go down, then he makes the kinetic energy go up. So in other words, if he brings those weights in, he's actually adding energy, kinetic energy, to the system. That energy has to come somewhere. It comes from the food and the chemistry that's inside the body that we were ignoring. On the other hand, if he moves the weights out so his I gets bigger, then his kinetic energy drops because his denominator gets bigger. Again, that's taking energy out of the system. Where's that going? Again, it's because you're not accounting for all the energies in the system in terms of the fact that this is a live, living object. Trees don't do this. Okay? Rocks don't do this. Trees are actually living, but rocks certainly don't do this. So the fact is we've left a lot of energies in the atoms that are moving around, and we haven't accounted for them. We'll come back to that later in a field of study called thermodynamics, which is in a later chapter. And we'll talk more about this idea of internal energy.